The Miracles of the Holy Spirit aquarium photographs present a specific challenge to standard models of visual noise. We are analyzing these images as a series of highly structured anomalies, where each geometric alignment presents a distinct mathematical problem. Looking at the secondary photograph, we can locate specific linear light patterns forming 1111. This repeating numeric signature requires a statistical explanation to determine its origin. To test for specified complexity, we look past normal randomness. Improbable events happen constantly, but when geometric shapes perfectly align with a pre-existing structure, we identify a clear signal. This gauge represents the 50-bit universal probability bound. Below this limit, chance is effectively ruled out. If the patterns captured in these photographs cross that 50-bit threshold, we have to evaluate the images within an intelligent teleological design framework. This model identifies 8 distinct specifications within the image data, ranging from the architectural symmetry of the 1111 light pillars to the biological structure of the SRY gene catalyst. By treating each match as a precise, independent event, we can assign a stochastic probability to each domain. To find the likelihood of all 8 independent domains converging simultaneously, we calculate their joint probability. Multiplying the individual chance of these 8 events produces an astronomically small fraction, 2.50 times 10 to the negative 24. We can translate that microscopic decimal into a measurement of information density using the Shannon entropy equation. The result is a profile containing 78.40 bits of information. Bringing back our universal probability bound gauge to compare, we see that the 78.40 bits from the aquarium image exceeds the limit of chance by 28.40 bits. Because the visual information density goes so far past a mathematical boundary of chance, the model treats these images as a highly compressed, intentional multi-domain signal. This scale sets up a Bayesian analysis to formally weigh the design hypothesis against chance. We start with entirely neutral, 50-50 prior assumptions to keep the test conservative. Now we apply the calculated likelihoods. The model assigns a 0.99 likelihood to design, and our calculated 2.50 times 10 to the negative 24 to chance. The resulting Bayes factor is 3.96 times 10 to the 23rd in favor of design. Consider how strong this mathematical evidence is. Even if you rigidly dropped your starting assumption for design down to a mere 1%, the weight of the evidence would still favor the design hypothesis. Standard fire consumes its fuel through high-entropy chemical reactions, but quantum electrodynamics allows for a different state, coherent resonance. In this model, the photon exchange is perfectly efficient, recycling energy without thermal loss, which keeps the local entropy change at 0. If the universe evolves toward a final singularity of infinite computational capacity, that point would function as a cosmic attractor. This omega point allows information to be projected backward through the timeline, providing a retrocausal mechanism for how this high-density signal appeared in a 2005 aquarium. The Bayesian math points toward intentional communication, while the omega point theory provides a proposed physical mechanism for how that signal arrived. You can manually test these calculations yourself using the interactive computational model linked in reference 14 of the source paper. In this Google Colab notebook, static text is separated from executable Python code blocks. Running the primary cell outputs exactly 78.40 bits of Shannon information. Stress test the model by reducing the cosmological probability and watch the Bayes factor dynamically adjust in real time. We've covered the 50-bit threshold for specified complexity, the Shannon entropy equation, and the Bayesian factor. Interacting with this data model allows you to mathematically verify the highly structured, non-random nature of the good faith paradigm on your own.